June 1944, somewhere in the hedgerows of Normandy. A Sherman Firefly sits hull down behind an earthen mound, its long 17-pounder barrel barely visible above the ridgeline. The crew is silent, breath held, watching a road junction 800 meters distant. The radio crackles. "Tiger, 2 o'clock. Coming your way." The gunner's hands are steady on the traverse wheel, but his mouth is dry. They all know the mathematics of this encounter. A Tiger's 80 meters can punch through their Sherman from over a mile away. They need to be close, uncomfortably close, to have any chance. But today, something is different. Stacked in the ammunition racks behind them are 5 rounds unlike anything they've fired before. No markings explain what makes them special. The brass at headquarters called them priority ammunition. Handle with care. Use sparingly. The rounds look odd, lighter than the standard armor-piercing shot, with a strange segmented jacket around a slender core. The loader doesn't understand the physics, but he's been told these rounds can do something impossible: kill a Tiger from the front. The German tank rounds the corner, 54 tons of steel, rumbling forward at the speed of a man's jog. Its armor catches the morning light, that distinctive Zimmerit paste coating, applied at the factory to prevent magnetic mines. The commander's cupola swivels, searching. The Sherman crew knows they have seconds, maybe less, before those German optics find them. "Load APDS," the commander whispers. "If you're watching this channel, you already know the Tiger wasn't invincible." But understanding how the Allies finally cracked the code of German heavy armor requires going back, not to the battlefield, but to a classified British research facility where metallurgists and ballisticians worked against the clock to solve a problem that was costing lives every day. This is the story of a shell that changed everything, a technological leap so significant that it remained classified even as it deployed to the front lines. The Germans had no idea what was hitting them, and by the time they figured it out, it was already too late. The problem that wouldn't die, Tunisia, February 1943. British tank crews get their first encounter with the Tiger was won in combat. The reports that come back to London are alarming. A Churchill tank, Britain's heaviest, fires 8 rounds from its 75mm gun at a Tiger from 150 feet. Every single shell bounces off the side armor. At longer ranges, the situation is worse. Crews watch their armor-piercing shot strike the Tiger's frontal plate and ricochet skyward, leaving nothing but a scratch in the paint. The Tiger Oi's frontal armor is 100 millimeters thick, nearly 4 inches of hardened steel. The gun mantlet is even thicker at 135 millimeters. This isn't just thick, it's quality steel, face-hardened and carefully heat-treated at the Krupp works. When a conventional armor-piercing shell hits this barrier, at anything less than optimal conditions, the shell itself shatters before the armor does. British intelligence collects the data from every Tiger engagement. They measure angles, distances, penetrations, and failures. The math is brutal. The standard 6-pounder anti-tank gun, the backbone of British anti-tank defense, can penetrate 84 millimeters of armor at 500 yards. That's enough for a Panzer IV. It's not enough for a Tiger, not from the front. The 17-pounder is better, capable of 120 millimeters of penetration at 500 yards. But that's still marginal against a Tiger's frontal armor, especially at combat ranges where dust, movement, and stress degrade accuracy. The Tiger doesn't just survive hits, it kills from distances where Allied tanks can't effectively return fire. In ideal conditions, the Tiger's 80mm PK-36 gun can penetrate 100 millimeters of armor at 1,000 meters. That's a mile away, a distance where most Sherman and Cromwell crews can't even identify the target clearly, let alone hit a weak point. The psychological impact is immediate. Tank crews begin to hesitate, to hold back, knowing that closing the distance means entering a kill zone where the Tiger has every advantage. The British Army's solution initially is numerical: Overwhelm Tigers with multiple tanks, accept the losses, and exploit the fact that Tigers are rare. But this is a doctrine of attrition, and attrition burns through trained crews at a rate Britain cannot sustain. There has to be another way. The tungsten solution. The answer begins with a metal most soldiers have never heard of, tungsten carbide. In peacetime, it's used for cutting tools and industrial drills. Its defining characteristic is density, nearly twice as dense as steel, and hardness that approaches diamond. When tungsten carbide strikes armor at high velocity, it doesn't shatter like steel. It cuts. The concept is simple in theory. Take a small tungsten core, a penetrator perhaps 50 millimeters in diameter, and accelerate it to velocities far higher than a full-bore shell. The kinetic energy equation is unforgiving. Energy equals 1/2 mass times velocity squared. Double the velocity and you quadruple the energy. That energy, focused on a tiny impact area, can punch through armor that would laugh off a larger, slower shell. But there's a problem. Tungsten is heavy. If you make a full-sized shell out of tungsten carbide, say 76 millimeters in diameter to fit a 17-pounder gun, it's too massive to accelerate effectively. The propellant charge would need to be enormous, generating pressures that would destroy the gun barrel. You can't make it go fast enough to matter. The breakthrough comes from an unconventional direction. What if the tungsten core doesn't have to fill the entire barrel? What if you could wrap it in a lightweight jacket, a sabot, that gives it the necessary diameter to trap the propellant gases, but then falls away after the shell leaves the barrel? The tungsten penetrator, suddenly free of its carrier, would fly onward at velocities no full-bore shell could match. The idea isn't entirely new. French and German engineers had experimented with similar concepts before the war, but making it work in combat conditions requires solving a cascade of problems. The sabot must separate cleanly and consistently within about 100 yards of leaving the muzzle. If it separates unevenly, the penetrator tumbles and the shot goes wild. The penetrator itself must be perfectly balanced. Any asymmetry at 1,000 meters per second produces dramatic dispersion, and the gun barrel must be immaculately clean. Fouling from previous shots can catch the sabot during separation, ruining accuracy. The race against time. By late 1943, the development is underway at classified British research facilities. The driving force includes General A.G.L. MacNaughton, a Canadian artillery officer from the Great War, who understands that technological superiority can compensate for numerical inferiority. The pressure is immense. Intelligence reports indicate the Germans are fielding a new heavy tank, the Tiger II, with frontal armor up to 150 millimeters thick and sloped at 40 degrees. The existing anti-tank guns are becoming obsolete before they even arrive in Normandy. The engineers work through iteration after iteration. Early sabots are made from aluminum alloy, segmented into 3 or 4 petals, held together by a forward centering band. The base contains a rubber obturator to seal the propellant gases, and a driving band to engage the barrel's rifling. When the shell fires, setback forces partially unlock the petals, but gyroscopic spin keeps the assembly together until it clears the barrel. Outside the muzzle, aerodynamic drag rips away the petals, and the base unit falls back, leaving the tungsten core to fly free. The tungsten penetrators themselves are marvels of precision manufacturing. Each one is turned on a lathe to tolerances measured in thousandths of an inch. The cores are encased in a thin steel sheath with a ballistic cap on the nose. The cap distributes the initial impact shock, preventing the tungsten from shattering. Behind it, a penetrating cap focuses the force onto a small area of armor. As the penetrator drives through, the steel sheath peels away, and the tungsten core continues inward, creating a catastrophic shower of armor fragments and molten metal inside the target tank. But tungsten is scarce. Britain imports much of its tungsten from China and Portugal, and wartime shipping losses make every ton precious. Each APDS round requires tungsten that could otherwise make a dozen cutting tools or 100 drill bits. The decision is made to ration the ammunition strictly. APDS will be issued to 17-pounder guns and 6-pounder guns only, not the 75mm guns that equip the majority of British tanks. Even with this restriction, supply will be limited. Crews will carry perhaps 5 to 10 APDS rounds mixed with conventional ammunition. They'll need to choose carefully when to use them. Silent deployment, June 6, 1944. D-Day. The invasion fleet crosses the Channel. Aboard the landing craft, Sherman Firefly crews check their ammunition loads. They have 17-pounder rounds, armor-piercing capped ballistic cap shells, high explosive, maybe some practice rounds for ranging shots. But they don't have APDS, not yet. The ammunition is still in England, awaiting final quality checks and distribution orders. The APDS rounds arrive in Normandy in late June or early July 1944, depending on the unit. There's no fanfare, no training films, no detailed briefings. Security is tight. The crews are told the basics. The round is lighter, faster, and penetrates more armor than anything they've fired before. It's less accurate at long range, so save it for medium distances, 500 to 1,000 yards, where penetration is critical. The rounds are marked with minimal identification, just enough to distinguish them from standard shot. The Germans have no warning. Their intelligence services, focused on tracking Allied divisions and estimating invasion timelines, have no idea that a technological shift has occurred. To them, the 17-pounder is a known quantity, dangerous but manageable, requiring Tigers and Panthers to maintain distance and use their armor effectively. The idea that a Sherman Firefly might suddenly possess the ability to penetrate a Tiger's frontal armor from 800 meters simply isn't on their threat assessment. The first engagements happen almost by accident. A Firefly crew cornered by a Tiger loads APDS out of desperation. The shot flies true. The Tiger shudders, smoke pours from the hatches, and the crew bails out. The Firefly crew is stunned. They've killed a Tiger from the front at a range where they should have had no chance. The report goes up the chain, but it's fragmentary, confused. One data point in a battlefield full of noise. The killing begins. As July progresses, the pattern repeats. Tigers advance into what should be safe engagement ranges and die with holes punched clean through their frontal armor. The penetrations are distinctive, neat entry holes often with the edges of the armor plate peeled inward, indicating an impact velocity far higher than conventional shot. Inside the tanks, the tungsten core creates havoc. Unlike high-explosive shells, which rely on blast and fragmentation, the APDS penetrator produces a jet of molten armor and core material that ignites ammunition, hydraulics, and fuel. Crew survivability in a successfully penetrated Tiger drops to near zero. German after-action reports begin to reflect confusion. Tank commanders report being engaged and penetrated from ranges where Allied tanks should be ineffective. The damage doesn't match the expected performance of 75mm or even standard 17-pounder ammunition. Some crews assume they've been hit by tank destroyers, which mount heavier guns. Others think they've encountered a new Allied heavy tank. The truth that existing Fireflies and towed 17-pounders now have the capability to frontally penetrate Tigers doesn't occur to them because it shouldn't be possible with the ammunition types they know about. The tactical implications are immediate. Tiger aces, accustomed to dominating the battlefield through superior range and armor, suddenly find their margin of safety has evaporated. A Tiger that might have advanced confidently to 800 meters to engage targets is now vulnerable from that same distance. The psychological effect is profound. Tankers fight as much with their confidence as with their weapons. When that confidence erodes, hesitation creeps in. Commanders second-guess decisions. Opportunities slip away. British and Canadian crews, meanwhile, gain a newfound respect for their Fireflies. The tank has always been awkward, top-heavy, cramped, with a gun so large it required cutting away part of the turret's interior to accommodate the recoil mechanism. But now it's a tiger killer, and that reputation transforms it from a liability into an asset. When a column of tanks moves up, the Firefly stays hidden as long as possible because the Germans have learned to prioritize killing it first. But when a tiger appears, the Firefly earns its keep. The limits of innovation. APDS isn't a miracle weapon. It has flaws that frustrate the crews using it. The first and most significant is accuracy. A standard 17-pounder armor-piercing shell follows a predictable trajectory. Gunners learn to compensate for drop and wind drift, and with practice, they can place shots consistently at 1,000 yards. APDS is different. The lightweight penetrator is more susceptible to crosswinds. The sabot separation, though designed to be consistent, introduces slight variations from round to round. At ranges beyond 1,000 yards, the dispersion opens up dramatically. A shot that should hit the target's center mass might miss entirely. Quality control is another issue. Wartime production, rushed to meet demand, doesn't maintain the tight tolerances that the ammunition requires. Some rounds have sabots that separate unevenly, sending the penetrator tumbling. Others have tungsten cores with microscopic flaws that cause them to shatter on impact instead of penetrating. Crews learn to trust APDS at medium range, but to remain skeptical at longer distances. The effective engagement range for reliable tiger kills settles at around 500 to 800 meters, closer than crews would like, but still far enough to survive if they shoot first and shoot accurately. Then there's the issue of post-penetration damage. A conventional armor-piercing shell, once it penetrates, fills the interior of the target tank with fragments and explosive force. The damage is catastrophic and immediate. APDS relies purely on kinetic energy. The tungsten core and the molten armor it produces are deadly, but they don't guarantee a catastrophic kill. Sometimes the penetrator passes clean through the tank, exiting the rear without hitting critical systems. The crew might be wounded or killed by the shockwave and spalling, but the tank itself might remain mobile. It's a killing wound, but not always an instant one. The scarcity of APDS remains a constant frustration. Even by late 1944, ammunition allocations are limited. A Firefly might carry 77 rounds total, but only 5 to 10 of those are APDS. The rest are standard AP and high explosive. This forces gunners to make agonizing decisions in the middle of combat. Do you use APDS on a Panther, whose frontal armor is thick but potentially vulnerable to standard shot? Or do you save it for a Tiger, gambling that one will appear before you're eliminated? There's no right answer, only choices made in seconds under fire. The Germans respond. By August 1944, German intelligence has pieced together enough battlefield evidence to understand that something has changed. Recovered penetrators, distinctive in their small diameter and tungsten composition, are analyzed. Engineers recognize the design, a discarding sabot round, similar to concepts Germany itself had experimented with. The Panzergranate 44, a German APFSDS round, is in development, but it won't be ready in time to affect the campaign in France. The German response is tactical rather than technological. If the Allies now possess ammunition capable of frontally penetrating Tigers at medium range, then Tigers must avoid presenting frontal shots at medium range. Commanders are instructed to engage from longer distances, where APDS accuracy degrades, or to maneuver for flank shots, closing quickly to minimize exposure. The problem is that Normandy's terrain doesn't cooperate. The Bocage, dense hedgerows and narrow lanes, forces close-range engagements where maneuver space is minimal. Tigers become trapped in environments where their advantages are negated and their vulnerabilities exposed. Crew training emphasizes vigilance. Fireflies are identified by their longer barrels and slightly different silhouettes. Orders are to eliminate fireflies first, before they can bring their 17-pounders to bear. But in the chaos of combat, identification is uncertain. By the time a commander spots a firefly, the firefly has often already fired. And if that first shot carries APDS, the engagement is over. August 1944. The weapon matures. By August, APDS is no longer a secret. Its operational ammunition issued widely to 17-pounder equipped units. Production has ramped up, though it still lags behind demand. Crews have developed tactics around its strengths and weaknesses. The optimal engagement range is understood, 500 to 800 meters, where accuracy remains acceptable and penetration is overwhelming. At these distances, APDS gives even a lightly armored Firefly parity with the heaviest German tanks. The 6-pounder anti-tank gun, nearly obsolete against Panthers and Tigers when armed with conventional shot, gains a new lease on life. APDS for the 6-pounder can penetrate 140 millimeters at 500 yards, more than enough to defeat a Tiger I's frontal armor. Suddenly, infantry anti-tank teams possess a weapon that can stop heavy armor without requiring close assault. Towed 17-pounders and 6-pounders, dug into defensive positions, become deadly ambush weapons. German tank commanders learn to fear roadside positions where a concealed gun might wait, loaded with ammunition that erases the Tiger's protective advantage. The American forces fighting alongside the British and Canadians take note. The United States has developed its own sub-caliber ammunition, HVAP, high-velocity armor piercing, using a tungsten core in a slightly different configuration. It's issued to 76 meters armed Shermans and tank destroyers. The performance is similar: higher velocity, better penetration, reduced accuracy at long range. American crews engage Panthers and Tigers with newfound confidence, knowing they have the ammunition to penetrate if they can land the shot. The human cost of technology. For every successful engagement where APDS saves lives, there are failures where it doesn't. A gunner misjudges the range and the shot flies high, alerting the Tiger to his position. The return fire is instant and lethal. A loader fumbles the unfamiliar ammunition in the stress of combat, and the precious seconds lost are enough for the German crew to fire first. A round with a manufacturing defect fails to penetrate, and the crew has no time to reload before the Tiger's 88mm replies. The Tiger crews, for their part, die without understanding what killed them. The APDS round gives no warning. There's no tracer to follow, no distinctive sound. One moment the commander is scanning for targets. The next, a tungsten core moving at over 1,000 meters per second punches through the frontal armor, and the interior of the tank becomes an inferno. Some crews bail out, burned and deafened. Others don't make it to the hatches. The myth of the Tiger's invincibility dies with them, one tank at a time. The soldiers operating the guns firing APDS rarely think about the metallurgy, the engineering, or the supply chains that brought this ammunition to their position. They think about survival. They think about the friend who died yesterday, when his Sherman took an 80-millimeter shell through the turret. They think about finishing the mission and making it home. The APDS round is simply a tool that gives them a fighting chance against an enemy that, until recently, seemed unbeatable. Villers-Bocage, a case study. The town of Villers-Bocage in Normandy becomes synonymous with Tiger tank combat. On June 13, 1944, elements of the British 7th Armored Division push into the town, only to encounter SS Obersturmführer Michael Wittmann and his company of Tiger tanks. The ensuing battle is chaotic, brutal, and emblematic of the challenges Allied forces face against concentrated Tiger deployments. Wittmann's Tiger ambushes the lead elements of the British column, destroying Cromwell tanks and half-tracks in rapid succession. The narrow streets and buildings restrict visibility and maneuver space, ideal conditions for a well-positioned Tiger to dominate. British crews scramble to respond. A Sherman Firefly, commanded by Sergeant Bramall, engages one of the Tigers at short range. The Firefly's 17-pounder barks, and the Tiger is hit. Whether the round is APDS or conventional shot, the report doesn't specify, but the Tiger is stopped, crew bailing out. The battle rages through the morning. Other Tigers are immobilized by infantry using Piat anti-tank weapons and engaged by towed anti-tank guns. Wittmann's own Tiger, despite its early successes, is eventually destroyed. Accounts vary on whether it was a Firefly, an anti-tank gun, or a combination that delivered the killing blow. The point is clear. Tigers are deadly, but they are not invincible. When engaged by coordinated forces with effective weapons, they die. Villers-Bocage becomes a learning experience for both sides. The British realize that charging armored columns into confined spaces without infantry support invites disaster, regardless of ammunition types. The Germans learn that even Tigers require combined armed support and cannot dominate through firepower and armor alone. APDS, arriving in the weeks following Villers-Bocage, shifts the calculus further in the Allies' favor. The next time a Tiger tries to hold a town, the Fireflies engaging it will have ammunition designed specifically to punch through its armor. Beyond Normandy, as the campaign in Northwest Europe progresses into Belgium and the Netherlands, APDS becomes standard ammunition for British and Canadian 17-pounder units. The Germans introduce the Tiger II, the King Tiger, with even thicker armor. The frontal upper hull is 150 millimeters at 40 degrees, equivalent to over 200 millimeters of vertical armor. Conventional 17-pounder shot struggles against this barrier. APDS, with its higher velocity and energy, remains effective, though margins are tighter and shot placement becomes even more critical. The arrival of heavier Allied tanks, the Pershing, the Comet, eventually the Centurion, begins to address the armor imbalance through vehicle design rather than ammunition alone. But these tanks arrive late in the war or after its conclusion. Throughout 1944 and into 1945, APDS is the primary method by which medium Allied tanks and towed anti-tank guns engage and defeat German heavy armor frontally. The Soviets, fighting their own battles on the Eastern Front, developed similar ammunition for their 85mm and 100mm guns. The BR-365K APCR round for the 85mm gun can penetrate the Tiger's side armor at 500 meters, though frontal penetration remains difficult. Soviet doctrine, however, relies less on technological parity and more on numerical superiority and tactical maneuver. T-34-85 tanks engage Tigers from the flanks and rear, accepting losses to achieve kills. The introduction of the IS-2 heavy tank with its 122mm gun provides another solution. A shell so powerful that even a near miss can disable a Tiger through sheer concussive force. The post-war legacy. When the war ends in May 1945, APDS technology doesn't disappear. It becomes the foundation for Cold War tank ammunition development. The British Centurion tank, entering service in the late 1940s, is issued APDS as its primary anti-tank round, with no conventional armor-piercing shot provided. This reflects a philosophical shift. APDS is no longer an emergency measure or a specialty round. It's the standard. The United States continues developing APDS and its successor, APFSDS, armor-piercing fin-stabilized discarding sabot, which replaces spin stabilization with fins, allowing even higher velocities and better accuracy. By the 1950s and 60s, smoothbore tank guns firing fin-stabilized penetrators become the norm. The lineage traces directly back to those early tungsten cored rounds delivered to Normandy in the summer of 1944. Captured German documents reveal that Germany's own APDS development, the Panzer Granate 44, suffered from the same challenges the British faced: manufacturing complexity, material shortages, and quality control issues. Had the war continued into 1946, German tanks might have fielded similar ammunition. But by late 1944, Germany's industrial capacity was collapsing under sustained Allied bombing, and exotic ammunition types took a backseat to simply producing enough conventional shells to keep the Wehrmacht fighting. The forgotten advantage. For all its impact, APDS remains one of the lesser-known technological developments of World War II. History's focus on radar, the atomic bomb, code-breaking, technologies that shaped the strategic level of the war. APDS operated at the tactical level, in the mud and hedgerows where individual crews fought and died. It didn't win the war, no single weapon does, but it changed the battlefield calculus in crucial engagements during the summer and fall of 1944, when the outcome in Northwest Europe hung in the balance. The crews who fired those rounds often didn't know what made them special. They knew the shells were lighter, that they were supposed to penetrate better, that they were scarce and shouldn't be wasted. The metallurgical science, the industrial effort, the security protocols that kept the ammunition's capabilities secret from German intelligence, all of that was invisible to the men loading the rounds and pulling the triggers. What mattered was results. When a Tiger appeared at 700 meters and you had APDS loaded, you had a chance. Without it, you relied on luck, maneuver, and numbers. With it, skill and timing could be enough. The Tiger Ace's perspective from the German side, the arrival of APDS represented an erosion of the qualitative edge that Tiger units relied upon. Tiger Aces, tank commanders with multiple kills to their names, built their reputations on exploiting the Tiger's superior armor and firepower. Tactics revolved around engaging from positions where return fire was ineffective, using the Tiger's optics and gun to kill Allied tanks before they could close to effective range. APDS disrupted this paradigm. Suddenly, closing to medium range was no longer safe. A Sherman Firefly at 800 meters, previously an annoyance, became a mortal threat. The Tiger's armor, previously reliable protection against anything short of a lucky hit or a flanking shot, could no longer be trusted absolutely. The psychological impact on German crews is difficult to quantify but shouldn't be underestimated. Confidence is a weapon. When it's shaken, decision-making suffers. Tiger Aces adapted where they could. Michael Wittmann, before his death in August 1944, emphasized long-range engagements and rapid position changes to minimize exposure. Otto Carius, another Tiger Ace, stressed the importance of infantry support and combined arms tactics, recognizing that Tigers operating alone were vulnerable regardless of their armor. But adaptation required time, training, and resources, all of which were increasingly scarce for the Wehrmacht by late 1944. Many Tiger Aces didn't survive to see the war's end. Wittmann was killed near Villers-Bocage, his Tiger destroyed in circumstances still debated by historians. Whether APDS was involved in his death is uncertain, but it's representative of the broader trend. The Tiger's dominance was temporary, and the Allies developed counters more quickly than Germany could escalate the arms race. The Engineers' War, the story of APDS, is ultimately a story of engineering under pressure. The British metallurgists and ballisticians who developed the ammunition worked with imperfect information, limited resources, and a ticking clock. They didn't have the luxury of years of peacetime testing. They had months, perhaps weeks, to move from concept to production. The challenges were immense. Tungsten carbide is brittle, too much shock, and it shatters instead of penetrating. The Sabot design required balancing aerodynamic stability with clean separation, too much resistance, and the penetrator veers off course. The gun barrels had to withstand higher pressures and velocities without premature wear. Each problem demanded a solution, and each solution introduced new problems. Yet they succeeded. By mid-1944, APDS was in production and deploying to the front lines. The ammunition wasn't perfect, accuracy issues persisted throughout the war, but it was effective enough to change battlefield outcomes. In the context of World War II's industrial and technological race, that was a victory. The German equivalent, Panzergranate 44, never reached the same level of deployment. German industry, stretched thin and under constant bombardment, couldn't prioritize exotic ammunition when basic production of tanks, fuel, and conventional shells was faltering. The Allies, with intact industrial bases in Britain and North America, could afford to invest in APDS production even as they maintained output of conventional munitions. Conclusion? The secret shell that made Tiger Aces helpless wasn't a single dramatic invention. It was the culmination of metallurgical science, precision manufacturing, battlefield feedback, and logistical effort. APDS arrived quietly, deployed without fanfare, and changed the war's trajectory in ways that only became apparent in hindsight. For the crews firing it, APDS was a tool that gave them a fighting chance. For the engineers who designed it, it was proof that ingenuity could overcome material disadvantages. For historians, it's a reminder that technological warfare is won not just by the weapons themselves, but by the industrial capacity, scientific expertise, and logistical networks that bring those weapons to the battlefield at the right time. The Tiger tank remains an icon of German armored warfare, a symbol of engineering excellence and combat effectiveness. But the Tiger's dominance lasted less than 2 years, from 1943 to late 1944. APDS, along with improved Allied tactics, heavier tanks, and overwhelming numerical superiority, ended that dominance. The Tiger Aces never saw it coming, and by the time they understood what was hitting them, the war had already turned. The next time you see footage of a Sherman Firefly or read an account of a Tiger destroyed from the front at 800 meters, remember the tungsten cord projectile that made it possible. Remember the metallurgists who solved the material science problems, the factory workers who manufactured the rounds under wartime conditions, the loaders who handled the ammunition under fire, and the gunners who placed the shots with seconds to aim. That's the human dimension of technological warfare. The machines matter, but the people matter more.